the last lesson in this set is marginal density of a bivariate normal distribution. So this was actually one of the integrals that motivated me to have this class in the first place, because I gave this in introductory statistics class to people who hadn't done calculus for quite some time, and pretty much everybody fell flat on their face. So hopefully if we go through this one time, I want to just point out some of the tricks that pop up quite often when we're integrating probability distribution functions, probability density functions. And this is a reasonably complicated and useful example. So if you thought the Black-Scholes formula was difficult, this one is, it's got the same number of variables, but they have Greek names, or at least 5 of them have Greek names, and so I think that makes people think it's more complicated. For the model I want to use, we can simplify it a bit. So what I would want to use this for, it's for 2 random variables, but rather than being independent, they're correlated. And so this last argument that I have here is a correlation coefficient. When it's positive, it just means if the first random variable, so if x were large, and I could observe that before observing y, that I would expect y to be large as well. If it were 0, then knowing the value of x wouldn't tell me anything about the value of y. And if it were negative, then if I knew I had a large value of x, that would lead me to expect a small value of y. If I want to use this in a financial application, the mu's, these are sort of expected values, so they would be expected return. And if I were using this for a single asset, I would sort of say that the expected return this period is probably going to be the same as this expected return in the next period. And then these sigma x and sigma y are thought of as the risk of owning that asset. So the sigma x would be the risk in the first period, sigma y would be the risk in the second period. If the periods are next to each other and reasonably short, then you can also get away with just assuming that that's the same. So I'm going to rewrite this with sigma x equals sigma y just equals sigma, and mu x equals mu y just equals mu. And that'll at least make this fraction in the right-hand side drop down one level, because I'll be able to take this sigma x squared will be the same as this product, sigma x, sigma y, and the same as this, so I'll be able to write that just down here. And then the thing that I'm trying to compute is called a marginal density. So this is the density, in theory, I have these 2 variables that are somehow behaving together. But if I'm in a position where I can't see the other variables, so suppose I don't pay attention to what happened during the first period, and I just wonder what's going to happen in the second period, that's the marginal density. So if I don't care about x, and I just say, what's the best you can tell me about y, given that I'm choosing to ignore x, you end up with this thing called marginal density. And you get that just by integrating one of the variables out. So if I take a function of x and y, and I integrate it from negative infinity to infinity with respect to x, I'm going to be left with this partial integral that's going to be a function of y. And that's going to be called, in probability and statistics, the marginal density of y. For this course, I'm just doing one partial integral. So let's see. So that was my example was, x and y were returns on an asset in consecutive periods. And then the simplification I'm going to make is that the expected return on the asset is the same in each period, and the risk that I'm taking on by investing in that asset during each period is the same. So I only have 1 mu and 1 sigma. And so I can almost force this onto one slide. So oops, have I done it the other way around? Yeah, so on the first slide, I said I was going to get the marginal density with respect to y. Here, I'm doing the same thing with respect to x, but it's exactly the same operation since it's symmetric with respect to x and y. So what I want to do is integrate this big, ugly bivariate density function from minus infinity to infinity with respect to y. And one of the nice things, so that I said this was the normal probability density function, it has this nice property that most of the time when you do things to it, the answer is a normal probability density function. So a good first step, and this happens quite often, you can usually make a pretty good guess as to what the answer should be. Or you can at least guess, what it should be if it's going to be easy to do. You might try that and find out it doesn't work, and then it's not going to be easy to do. But in this particular case, I'm just going to guess that the marginal density is just a univariate. So this is the same phi function. It's just been scaled by a factor sigma and shifted by a factor mu. But this is a normal probability density function. And so here, since I'm integrating with respect to y, everything in this marginal density with respect to x is going to be constant with respect to this integration. So what I'm going to do is factor all of that stuff out of here, move it outside of my integral sign, because if it's constant with respect to y, it can cross the integral sign, and then look at what's left and hope that that's something that I can figure out how to integrate. So the idea is that I will end up with this marginal density, my guess at what the marginal density function should be, times everything that's left. So this c here is this thing here with the 1 over square root of 2 pi sigma factored out. I just couldn't fit everything into the slide if I did it. And then I have all of this stuff left over. And so I need to somehow show that this integral from minus infinity to infinity, this big ugly mess dy, is equal to 1. And so this is what this value of c is equal to. So it's, if you multiply this by c, you just get the scaling factor from the bivariate density function.
Can we go back
Oh.
just real quick?
Yep.
I'm sorry. So you're taking your guess for what f of x will be and multiplying it by what we have up above. Is that what's going on?
So what I've done, I've taken this term here, or this factor here, and I've split it up into this and this. All right, so if I multiply those together, I get this thing back. And then this is what I want to appear outside. Oh, and again, this should be an x. It should be the same as this, just with the opposite sign. And so if I have a negative 1 here and a positive 1 here, that would be e to the 0. So it's basically what I've just done is multiplied this thing by 1, but used a clever choice of 1.
Thank you.
Okay. So now what I want to do is look at the part that's in the square brackets. So if I go back, I'm looking at this square brackets here. I want to simplify that. So this is the bit in the square brackets. If I wanted to do this subtraction, then I've got 2 sigma squared in the denominator here, and 2 sigma squared times 1 minus rho squared in the denominator here. So I need to multiply this first term by 1 minus rho squared over 1 minus rho squared. So if I do that, then I can put everything over a common denominator. And I have 1 minus rho squared times x minus mu squared, and then what I had originally. And if you look at this carefully, I have 1 times x minus mu squared minus x minus mu squared. So this 1 is going to disappear. This whole term is going to disappear, and what will be left is negative rho squared times x minus mu squared. So let's hope that that's what I've done in the next step. Yep. So I have negative rho squared times the quantity x minus mu squared. I have everything else still staying the same here. And let's see, what have I done? So now I multiplied the numerator by -1, and then I'm going to cancel that out by multiplying the whole fraction also by -1. So that made my first term positive, second term negative, third term positive. And if you stare at this for a while, it should start to look familiar. So if you think back to the completing the square lecture, you'll actually realize that this is already in the right form to be written as something squared. And that something is just going to be rho x times the quantity x minus mu minus y minus mu squared. Or sorry, minus y minus mu. Hopefully I'll get it right when I hit the next key. So I have rho times x minus mu. When I square that, I'm going to get this. Then I have minus y minus mu. When I square that, I'm going to get this. And then the cross terms are going to be rho x minus mu, y minus mu, with a negative sign in front of it. I'm going to get two of those from the outer and from the inner. And so that's where this middle term is coming from, or going, I guess. Okay. And then I'm going to write this. So it's exactly the same thing. I've just sort of rearranged where I'm putting parentheses. So I have y minus something, and that something is mu plus rho times x minus mu. So all I've done here, I had a rho times x minus mu, and a minus y. So I did something that's a bit clever here. Since this is squared, I can multiply the inside by -1. So I can actually write this as y minus mu minus rho times x minus mu. And when I square that, the -1 will go away. So it'll be -1 squared times the product here. So that lets me put this term in front and this term second. So I end up with this y, minus this mu. So this mu here becomes this mu here. Then I have minus rho times x minus mu. But since I'm writing it in these parentheses here, that minus has to be a plus because the minus is going over here. So I end up with mu plus rho times x minus mu. So that's mostly just an exercise in bookkeeping for signs. And then in the denominator, I'm going to write sigma squared times 1 minus rho squared as sigma times the square root of 1 minus rho. I'll put that all in parentheses and square that. And now if you look closely at what this is a variable minus a constant squared over 2 times another constant squared. And now I'm going to plug this back into my square brackets here. So this is what we had at the end of 2 slides ago. This was a thing where I said I want to show that this integral is equal to 1. And I want to look just at the integrand. So that's the c times the thing in the square brackets. So on the previous slide, I found another expression for what's in the square brackets here. And that's I've plugged in here. And then in my c constant, I'm going to do the same thing I did. I'm going to write the sigma times the square root of 1 minus rho squared in parentheses. And now this constant here is equal to this constant here. And if you think back to what did the normal density function look like, in the original one, this was called sigma. I just had a 2 sigma squared over in the exponential part of the function, and I had a 1 over the square root of 2 pi times sigma. So this is just a new value for sigma. And then in the numerator of the exponential part, I had y minus mu squared. And so now I just have y minus something, but I'm integrating with respect to y, and this doesn't have any y's in it, so that's effectively a constant. So this is actually a normal probability density function, just with a different mean and a different standard deviation. So this term down here is the standard deviation, and this term here is the mean. And so if I let m equal this guy here, which is that, and I let s equal sigma times the square root of 1 minus rho squared, which is that, then when I plug those in, I end up with 1 over the square root of 2 pi times s e to the minus y minus m squared over 2s squared. And this is exactly the normal density with mean m and then standard deviation s. And so if I integrate this, so I'm integrating this with respect to y from minus infinity to infinity. I know it's a density function. So this is sort of the big trick, is I don't actually have to do the integral if I can show that it's a density function, because I know every density function is going to integrate to 1. So the integral of this normal density over the entire real line, so from minus infinity to infinity, is equal to 1. And so now if I go back to, so this was my big ugly formula. I've just been simplifying and simplifying the integral. And now I have it, looks like the dy disappeared off the end of the slide. But the integral of this density over the entire real line is equal to 1. So I get that my marginal density was equal to 1 over the square root of 2 pi sigma. This is just the thing that I guessed and factored out at the beginning. So it looks like I switched the x and y's again. So this should be an x. So x minus mu squared divided by 2 sigma squared. So I get that the marginal density of x is also a normal distribution.